A neuron is made up of an affine transformation for linear relationships and an activation function. What exactly is the role of an activation function within the neuron? In the last lecture, we spoke about the affine transformation, which allows you to model linear relationships. The affine transformation is, of course, just one of the two functions that a single neuron applies to its inputs. And we've seen the affine transformation earlier when we spoke about linear regression. Let's say you have a set of points and you have a single neuron. You can then model a linear relationship using this single neuron. This single neuron is, of course, made up of the affine transformation and the activation function. If it's a linear relationship for linear regression, this activation function is simply the identity function, which means the input that it receives, it simply passes along to the output. This is when you set activation is equal to none. This is a parameter that you'll specify when you construct a layer of a neural network which has no activation for its neurons. It passes the output of the affine transformation to its output. The output of the identity function is simply the output of the neuron itself. Such neurons, because they understand only linear relationships between the input and the output, are also called linear neurons. Now, linear regression with one neuron require the identity function. In order for you to perform logistic regression with one neuron, this identity function was replaced by the softmax function as the activation. And the softmax function output two probabilities. The probability that the output y was equal to true or equal to 1, and the probability that the output was false or equal to 0. The predicted label in our logistic regression model was basically whichever of these two had the higher probability. If p of y is equal to true was higher, the output was predicted as true. If p of y is equal to false was higher, the predicted output was false. The input to this softmax function was the output of the affine transformation, that is w1x plus b1. The softmax function then outputs two probabilities based on this logistic formula. Once again, the details of this formula has been covered earlier. We won't dwell on it too much. This is the formula which gives us probability of y is equal to true. And here is the formula which gives us the probability of y is equal to false, which is 1 minus the probability that the output y is equal to true. Notice that the softmax function has its own weights and biases, that is W2, B2. When we discussed logistic regression, we spoke about softmax as one of the activation functions that can be used with a neuron. And we also spoke about the shape of this softmax function, also called the logit function. Formula for logistic regression results in this S-shaped curve, also called the sigmoid curve. And this S-shaped curve basically has points clustered around 1 or 0. The probability output of the softmax function can lie anywhere along this curve. That is, it can be anywhere between 0 and 1. And it's for you to define a threshold. If the probability value is above this threshold, the predicted label is 1 or true. If the probability value is below this threshold, the predicted label is 0 or false. If you think about the S-shaped curve for the softmax activation, it makes a lot of sense when your classification is binary, true or false, 0 or 1, and so on. But softmax can also be used for N category classification. Let's say you're classifying images as cats, dogs, birds, horses, etc. You can imagine that you can have any number of categories. Or if you're classifying handwritten digits using the MNIST database set, you'll have 10 categories. By using a number of binary classifiers together, you can perform N category classification. Let's take the specific example of digit classification where there are 10 output classes. You can train a one versus all classifier. So you'll have 10 binary classifiers. Each of these classifiers is a zero detector, which detects zero or not zero, a one detector, which detects 1 or not 1, a 2 detector which detects 2 or not 2. You can compare the outputs of all of these binary classifiers. All of these will be in the form of probabilities, and the actual predicted label is the output of the detector with the highest score. If the highest score is achieved by the 5 detector, the probability is that the output is 5, and that will be our predicted label. Another way by which we can use binary classifiers for N category classification is the one versus one method. For 10 possible predicted labels, you'll have to train 45 binary classifiers. Let's see how we get this number. Here you'll have one binary classifier for every pair of digits. So you'll have a classifier which detects whether this digit is a 1 or a 2. A classifier for 1 versus 3, 1 versus 4, and so on. So for n labels, you need n multiplied by n minus 1 divided by 2 classifiers. The 1 versus 1 binary classifier you can think of as a dual of digits, and the predicted label is the output of the digit that wins the most duels. If you find that the digit 2 wins the most duels against other digits, that is the predicted label. When we studied regression models, and even now, we've spoken of the activation function in very specific terms. We spoke about logistic regression and softmax activation, and we've seen how a binary classifier can be extended to classify in n categories. However, this activation function is not limited to the logistic or the softmax functions. In fact, softmax is just one of many activations that you could apply within a neuron. Here are a few activation functions that you could use for your neuron and the corresponding curves that they represent. One of the most popular ones is the ReLU function, which stands for rectified linear unit, which has a curve which looks like this. The y value is 0 for all x values below 0, and the y value is equal to the x value for values above 0. In addition, you also have the logit function. That's the one that we saw. That's for softmax activation with an S curve which goes between 0 and 1. You can also have the hyperbolic tangent as an activation function. Once again, it's an S curve which ranges from minus 1 to 1. Another possible activation function is the step function, which clamps the output to either minus 1 or 1. These are some of the choices that you could make to specify the activation function for your layer of neurons. These choices drive the design of your neural network and are critical in determining how your neural network performs. So make your choice of activation functions sensibly and with some thought. You might have understood by now that machine learning is part science, part skill. Tweaking your activation functions to get better performance is generally par for course. It's something every data scientist does. One of the most popular activation functions that you'll find out in the real world, and we'll use it a lot in our example programs as well, is the ReLU activation. It stands for rectified linear unit. The form of this function is simply the maximum value of the output of the affine transformation, that is wx plus b, comma 0. That means any negative values are clamped to 0 and positive values remain the same. Another commonly used activation function is the tan h, or the hyperbolic tangent. This is again an S-shaped curve. It's continuous and differentiable. These are important characteristics of activation functions because this gradient of the activation function is what we use when we perform gradient descent optimization that you studied when you studied regression models. The output of the tan h ranges from minus 1 to 1, which means it's centered around 0. So each layer's output is normalized around 0, which is a good thing for neural networks, as you'll see in a little bit. Having normalized output from layers of neurons greatly mitigates the problem of vanishing and exploding gradients that neural networks suffer from. Another common activation function, which we've already used in logistic regression, is softmax activation. The output ranges from 0 to 1. It's again an S shaped curve. This output is often interpreted as a probability. You find a probability number between 0 and 1, you specify a threshold, and you assign the predicted labels based on whether the probability number was above or below that threshold. This curve here is also called the logit curve. The activation function by itself might seem very simple, but what you choose for activation drives the design of your neural network. It's crucial in determining how your neural network performs. You'll understand this a little better when we understand how we train a neural network, the entire process, and how it works. For now, it's enough for you to understand that the combination of the affine transformation along with the activation function makes a neuron powerful, gives it the ability to learn arbitrary relationships. And all of these neurons, thousands of them put together in the form of layers, allows neural networks to perform almost magical stuff, solve complex machine learning problems. A neuron with no activation function is a linear neuron and can only learn linear relationships between its input and the corresponding output. In order for a neuron to learn more complex relationships, arbitrary curves, and other such, we require the activation functions. The most common activation functions which are popular are the ReLU, that is the rectified linear unit, the hyperbolic tangent, and the softmax function.